Hello everyone. In this video, I would like to show you some math behind the backpropagation algorithm introduced in Andrew's online machine learning course. As mentioned by Andrew, this is not required for beginner, but if you are curious, or if you just can't believe the algorithm unless you see the step-by-step proof, then I hope this video can give you some reference. Now let's get started. When I learned machine learning following Andrew's video, I'm not quite understand about these two slides. I mean, they looks correct, but I feel like there are at least these 5 following questions that prevent me from understanding properly. First of all, I would like to understand why the derivative of z3 can be represented as a3 multiplied by 1 minus a3. And secondly, why the delta can be represented in this way. And thirdly, as mentioned later in Andrew's video, he defined the delta I over L plus 1 as partial j partial zi over L plus 1. So if delta is this, how can we directly write delta j4 as shown above? And I also wonder why we have this and why we have this. Before moving to details about those questions, let me first refresh you about the forward propagation and some definitions. So first of all, we can imagine an input and an output for each neuron. The input can be represented as z and the output would be a. So if you want to go from z to a, you would have a equals to gz equals to 1 divided by 1 plus e negative z, which is known as the sigmoid function. And if you want to go from a to z, then you would have z equals to theta ta plus b, where b is the bias term. Taking this neuron as an example, we know that it's the first neuron in layer 3, so the input can be written as z31. The output would be a31. Okay, now if you look at the top left of the screen, I will leave all these definitions for your reference. The first question is why can we write the derivative of z3 as a3 dot multiply by 1 minus a3. To calculate the derivative, we have u divided by y derivative equals to u prime v minus uv prime divided by v squared. So same in here. If you want to calculate the derivative to z3, we can write it as 1 over 1 plus e negative z3 prime, which is equal to the derivative of 1, which is 0, minus the derivative of 1 plus e negative z3, which is negative e negative z3. And then the square of v, which is 1 plus e of negative z3 squared. So this can be simplified as z e of negative z3 divided by 1 plus e of negative z3 squared. On the other side of the equation, a3 dot product 1 minus a3 is equal to 1 over 1 plus e negative z3 times 1 plus e over negative z3 minus 1 divided by 1 plus e over z negative z3, which is equals to e negative z3 over 1 plus e negative z3 squared. So as you can see, these two are identical. So we can say that g prime z3 can be written as a3 dot multiply 1 minus a3. So similarly, we also have g prime z4 equals to a4 dot product of 1 minus a4. Now, in order to derive the second question, which is why delta 3 can be written as theta 3 transpose multiplied by delta 4 times the derivative we had before. We would have to handle the third question first, which is why we can write delta 4 as a4 minus y, given that the definition of delta il plus 1 is partial j over partial z il plus 1. So since we have a4 equals to h theta x j, which is the cost function, equals to y log a4 plus 1 minus y log 1 minus a4. Then we have partial j partial z4 equals to partial j partial a4 multiplied by partial a4 partial z4 according to the chain rule. So this can then be written as y divided by a4 plus 1 minus y times negative 1 divided by 1 minus a4 times the derivative of z. As for this part, I'm actually using an equation that the derivative of log x is equal to 1 over x. And as you might notice, the derivative of a4 over z4 is just g prime z4. So then this can be written as y minus y a4 plus y a4 minus a4 divided by a4 times 1 minus a4 multiply by this derivative, which is same as a4, the product of 1 minus a4, as we proved earlier. So this can then be simplified to y minus a4. Now, one thing I don't really quite get is whether a4 minus y and y minus a4 here matter, because from my point of view, they should be the same since they are describing the relation of the difference between y, the actual value, and the a4, the predicted value. Leave your comments below if you have any suggestions or ideas about whether this matter or not. So now we can take a look at the second question. Why is this one correct? Based on the definition of delta showing on the right, we have delta 3 equals to partial j partial z3. So, sorry, I need to add the index here. So this one, using the chain rule as well, can be written as partial j partial z 4k partial z 4k over partial a3j, and then partial a3j partial z3j. So I want to talk a little bit more here to help you understand why there is a submission here. Let's assume that we have a neural network like this. So if here is our layer 3, and here is the layer 4, or the output layer, we know that delta is actually describing the relationship or how many weight, how many influence a node contribute to the final cost function. So let's say we have a cost here. Then for each j in layer 3, for example this one, we can write it as zj3, where j equals to 1 in this case. So during the forward propagation, it contributes to both this node and this node. So when we do backpropagation, we also need to consider both this one and this one. That's why we have the summation over k here. So now let me change a color to show you what it looks like for backpropagation. Since we already have the j here, we first need to see how many inference the j get from these two input of the last layer of node. So this one can be written as z41 and this is z42. Now in order to get this, we have a coming out here, which is a3j, where j equals to 1 as well. So that's why we get this equation. The first derivative, partial j partial zk4, where k equals to 1 and 2, describe the inference of these two dark arrow. And then the second partial derivative, describing the relation from aj3 to z1, 4, and to z2, 4. And lastly, the third derivative is the partial from z33 to aj3. So then this can be written as summation of k partial j partial z4k, which is delta 4k. And since z can be written as theta a plus b, we can write the z out as partial of theta kj in layer of 3 times a3j plus the bias term in the layer of 3, divided by partial a3j. And the last one is nothing but the derivative to z3j. This one is equals to summation over k delta k4 theta kj3 g prime z3j. So if you do the vectorization, it becomes delta 3j equals to theta 3 for all rows but j column transpose delta 4 dot product of g prime z3j. Since for all the node in layer 3 we have this delta representation, we can then make it as a vector operation, which is delta 3 equals to theta 3 transpose delta 4 dot product of g prime z3. Alright, two more left. So the fourth question is why we can have the partial j partial theta ijl equals to the alj multiplied by delta l plus 1 I. Why this is correct. This can also be derived using the chain rule. So partial j theta partial theta lij is equal to partial j theta partial z I l plus 1 multiplied by partial z I l plus 1 divided or partial theta l ij. And this can further be written as partial j, we keep the first term unchanged, partial I l plus 1, but we make the second term a little bit clear theta ij L AL J plus BL, which is the bias term again, partial theta Lij. Now, as you can see, the first term is just delta I L plus 1, and the second term is just ALJ. Now, although the order is different, but since these two are values, so as they multiply each other, the value will be the same. Now, lastly, we need to prove that why we have the partial theta IJL equals to big delta IJL. If we already have 4, why do we need 5, and why is correct? So if you look at the slide earlier, we can see that actually the big D, the big delta, is the mean of all the submissions among all the samples for the AJL multiplied by delta I L plus 1 term. So let me make it more clear. We have delta IJL equals to the summation of K equals to 1 until M AJL delta I L plus 1, where M is number of samples. So to get the partial J partial theta IJL, sorry, I missed the J here. These need to be divided by M to get the mean value, or get the average for all the samples. That's why we have this equation here. And remember that when we have this equation, there are actually two equations here. One is without the bias, and one is with the bias. So until now, we assume that the cost function is written as y log h theta x plus 1 minus y log 1 minus h theta x. However, the actual j theta, which is the actual cost function, has one more term, which is where we do the regularization. It contains the theta here. If we just ignore this index to make it clear, then we need to handle this term for thetas that is not biased. So how to add this one into the above function? If we take only the partial derivative of this term for each theta, IJL, same as what we have in here, then we see that it's equal to 2 times lambda over m theta IJL, which is lambda divided by m theta IJL. So that's why in the slide we finally have the two form of D here. DIJL equals to m divided by 1 divided by m delta IJL if j equals to 1, which is the bias term, and DIJL equals to delta IJL divided by m plus the lambda theta IJL if j is not equal to 0, which means it's non-biased. Now for here, I'm thinking in the video it means the term divided by m, but since anyway this value is a parameter you are going to turn when you're actually using the backpropagation, so it doesn't matter that much. But leave your comments to let me know if you think this matters or not.